At this point, we've seen the first law of thermodynamics, rules that tell us how much energy is transferred into or out of a system and how to account for the conversion between heat and work during different processes. We've also discussed the second law of thermodynamics that establishes that energy will transfer spontaneously into or out of a system and its surroundings when the exchange increases the total entropy of the universe. The third law of thermodynamics establishes a way to determine absolute entropy so that we can calculate the standard reaction entropies for a greater range of systems. And now that we have these tools, one of the questions we might ask is how much energy could we extract to use as work from spontaneous processes? For example, how much of the energy released during combustion can we use to drive machines or to do electrical work? We've seen that for every process, the change in entropy of the universe is equal to the change of entropy in the surroundings plus the change of entropy of the system. The entropy change of the surroundings can be determined by the negative change in enthalpy of the system at a given temperature for the majority of chemical reactions that occur in the lab and in the world, plus the change in system entropy we can calculate according to the standard entropies of the products and the reactants. This gives us a relationship between the enthalpy of the system, a first-order concept, and the entropy of the system, the second law concept, supported by the third law relationship between entropy and temperature. We can further simplify this by dividing all terms by the negative temperature. So we have the negative temperature times the change in entropy of the universe is equal to the change in enthalpy minus the temperature times the change in entropy of the system, to give us a new function, again entirely composed of state functions, which makes it also a state function. And we see that it's given in units of energy. This is what we'll use to define Gibbs energy, what we used to call Gibbs free energy, and we give it the label G. Now let's look at how it behaves. When the change in entropy of the universe is positive, the change in Gibbs energy is negative, and the process is spontaneous. When the change in entropy of the universe is negative, the change in Gibbs energy is positive and the process is non-spontaneous, or the reverse process is spontaneous. When the change in entropy of the universe and the change in Gibbs energy equals zero, the system and the surroundings are at equilibrium and neither process goes forward. But what does this mean? Well, Gibbs energy tells us the maximum non-expansion work that can be drawn from a spontaneous process, or it tells us the minimum amount of work that we have to overcome in order to drive a non-spontaneous process forward. We can also see that delta G is temperature dependent. This lets us determine the temperature at which a process becomes spontaneous or becomes non-spontaneous. Let's look back at the melting ice. Sure, it's spontaneous at room temperature, but below 0 degrees Celsius, melting becomes non-spontaneous, and the reverse reaction becomes spontaneous. Water spontaneously turns to ice. At the freezing point, the forward and reverse processes are at equilibrium. If it's at equilibrium, delta G equals 0, so delta H equals T delta S, or the temperature equals the change in enthalpy per change in entropy. The enthalpy of fusion of water at 0 Celsius is 6008.837 joules per mole, and the entropy of fusion is 21.998 joules per mole Kelvin, which means that the temperature at equilibrium is 6008.837 divided by 21.998, and that equals 273.15 Kelvin, or the freezing point of water. And so Gibbs energy can be used to tell us the temperature at which these phase changes are going to take place. It can also tell us how much energy we can draw from different systems at different temperatures and under different conditions, which, as you'll see, comes in extremely useful when we're trying to determine whether a substance is acidic or basic, whether it's going to dissolve in solution or form a precipitate, or whether we can use it to drive electrical work, which, as it happens, are the remaining 3 topics in this year. So even though we've come to the end of thermodynamics as an independent unit, Remember that these concepts are going to keep showing up in everything we do for the remainder of the term.